Visible, sir. Screen is visible.
Invisible. Okay.
Yes, yes.
So today, as said, we would talk about how we can detect outliers in a data set. Data outlier detection. And the criterion that we would be using is called Sauvener's criterion.
Sir, if I'm allowed to ask, can you brief a little bit on data outliers? What it is?
Yeah. I'm going to brief about that. So when you do experiments, it is not very uncommon to find, spurious data points that basically do not conform to the central tendency of the data, right? We talked about central tendency of the data. That means if you take, 20, 100 measurements, most of the data tend to follow the central tendency. That means the normal distribution curve, which says that most of the data is going to fall around the mean value, right? But there will be some data points which are going to fall maybe far away from this data set. Typically, you do not. Sometimes you uh, do encounter this kind of spurious data points, and they could occur due to various reasons. I mean, maybe there is sudden influence that is coming from some other source while you are doing experiment, or all of a sudden there is something, your instrument starts malfunctioning, or there is something that goes wrong at that instant. So you can have this kind of spurious points. Okay. So basically, by if you have these spurious data points in your data, when you do your statistical analysis to estimate mean and standard deviation, they basically give incorrect estimation of these statistical quantities like mean and standard deviation can really be overestimated or underestimated. Okay. So it is important for that reason that we get rid of these spurious data points from the data set that you use to do the statistical quantification of your data, right? So, I mean, as I said, these could be for various reasons, but these are measurement glitches. So it is important to first detect them or identify them and then remove them from the data set to before we actually do the statistical quantification of the data, right? So let's talk about how we approach this using this criterion called Sauvener's criterion. By default, Sauvener's criterion assumes that the data that you have follows the normal distribution curve, and you are basically looking for the outliers. Okay. So let us define a quantity which is Z0, and the Z0 is basically xi minus x mean divided by Sx. Here, this xi is basically the suspected outlier. In a data set of, let's say, n different measurements, okay, n different data points. So according to Sauvener's criterion, the data point is a potential outlier. A data point is a potential outlier if it satisfies this condition, which is 1 minus 2 probability of Z0 is less than 1 over 2n. Okay, so mathematically we say that okay, if you have a data point and gives you some value of Z0, and you can find the probability of occurrence of that Z0 because you have the normal distribution table. And if 1 minus 2 p of Z0 is less than 1 over 2n, if this condition is satisfied, then that particular data point is an outlier. Okay, so this is mathematical, but what does it mean? It means that the outliers have less than 1 over 2n probability of occurrence. Okay, so it means that outliers have less than 1 over 2n probability of occurrence. That means if you have this Z distribution curve, so you have Pz and this normal distribution curve. So you say that probability of occurrence within this data range, let's say Z0 minus Z0 is Pz0. So you are basically talking about these regions where the outlier is going to lie. That means this region of the data. Okay, so the outliers are basically less than 1 over 2n probability of occurrence according to the Saviner's criterion. So mathematically, you have to check for this. 1 minus 2 of Pz0 should be less than or equal to 1 over 2n. Okay, so let's take an example and try to clarify this, understand this better.
So the outlier will always be falling outside of his boundary now, whatever you drawn, right?
Yeah. It will
So-
always fall outside. Yeah.
Fine. Sir.
So let us take this example, which will clarify your doubts if you have. So let's take this example. So let's say we have we are measuring pressure of a tire, and we have 10 different measurements. Okay, and from the 10 different measurements, we want to detect if there is any outlier. Okay, so I would note down the data points here.
Sir,
Yeah.
One doubt, sir. Sir,
Yeah.
like you mentioned just now that data point means if it is outlier, it will go away from the that region. Suppose that trend, suppose if the trend is increasing, but all of a sudden we get a reading where the next data should increase, the next data point should increase, but instead of that, it is going negative or it is decreasing in a high value. So that will not be an outlier. That cannot be an outlier. Sir.
See, an outlier, so a data point is an outlier or not an outlier. You basically have to decide at the end of the collection of the data, right? You take the entire data set and then you check for this condition here. this condition that you see here,
Yes.
you check for each and every data point, and if this is satisfied, then that data point is basically potential outlier. Okay, so it basically, depending on your probability, you define a region in which you expect your 95% or 99.7% data to lie. But if it is falling outside that range, you basically call it an outlier. Okay, so let's take this example to clarify your doubts, if you have. Let's say you have 10 data points. Just 1 second, I think they have switched off the AC, and I'm just asking them. Give me 1 minute. Really warm, you know.
Yes,
It is everywhere.
sometimes it will problem like that.
Okay, okay. Fine.
Yeah.
We'll see.
Yeah.
Thank you. Okay, so I just note down the data points. So let's say this is the pressure that we measure. Okay, so this is the data set that you have. Okay, just by looking at the data, you can sort of think that, I mean, this data may be a potential outlier. Okay, but how do you know that it is an outlier? You cannot just like that throw away the data points. You have to use some kind of statistical technique. And so that technique is basically the Sabonis criterion that we are discussing here. Okay, so for using this technique, we have to find the mean. So mean is basically xi divided by n. So if you add all these xi's and divide by n is basically 10, you can find the mean to be 27 psi. You can find out standard deviation. Standard deviation will come out to be 3.8 psi. Now, if you look at the Sabonis criterion, what does it tell you? Sabonis criterion tell you that if for a data point you have 1 minus 2 p z naught less than 1 over 2n, then the data point is a potential outlier. So in this particular case, your n equal to 10. So that means 1 over 2n is basically 0.05. So you are going to say that for any data point, if 1 minus 2 p z naught is less than 0.05, then that is an outlier. Okay, so we make a table for all these data points. We find out Z0 and PZ0. Okay, so let's say if I want to write down again, or I can just make a table here. So I find Z0, right? So what is the definition of Z0? Z0 is xi minus x min divided by sx. I take mod of that so that everything is positive. Okay. So for each one of these, I calculate Z0 because I know, I mean, this is xi. I have calculated the mean and I have calculated the standard deviation. So I can find out Z0, right? So for each one of these, I find out. So for I equal to 1, this is 0.263. This is 1.052. This is 0 because it is same as the mean. This is 0.263. 6.
So your screen was
Yeah. Something went wrong. I don't know. All of a sudden. Okay.
Okay, sir. We'll wait.
I think it didn't. Everything got erased, so I have to write again. There was some problem in the computer.
We'll wait, sir.
Are you able to see my screen?
No, sir.
Oh, I think maybe there was some connection issue or something. Just let me try.
Yeah, it is coming, sir.
It's coming, huh? Okay. Yeah, everything got erased. So I need to write again. So I found out all the Z0 values, okay, and then I can also find out the corresponding PZ0. Okay, so I am just doing the table here for all 10 values. So, okay. PZ0. So how do I find PZ0? So I have Z0 here. Then I go to the normal distribution table that we had seen last class. Let me show you that. The Z table, if I open, okay, you won't be able to see it, right? I will share my screen, entire screen. Okay, so now if I look at the first, your Z0 is 0.263, right? So you go 0.2 6. That is, you are approximating. Okay, you have to really interpolate between 0.06 to 0.07 because it is 0.26 and 3. I'm just approximating as 0.26. So I write it as for 0.263, it is 0.1026. Similarly, 1.052. For 1.052, I can go here 1.05. So again, you have to really interpolate, but I'm just approximating as this 0.3513. So you can note down for all the values. Okay. So for 0, it is basically 0, right? And for 0.263, already you know 1026. Then 0.526, right? So 0.52, I approximate as 0.1985. Then 0.789, 0.789, approximate as 0.78, 0.79. So it is 0.2852. So 0.2852. 0.526 was 0.1985. 0.263 was 0.1026. Now 2.368. 2.368, 2.3 around 0.4909 to 0.4911. Okay, so if you interpolate around 0.4910, so 0.4910, and when it is 0, it is 0. Okay, so then you have to find 1 minus of 2 pz naught, right? So you can find out for all these values. I'm just writing here. I believe is this. So I'm doing the table here. One minus 2. Already you have found pz naught. So 1 minus 2 pz naught you can find. So if you find, you will find that this value is going to be 0.018. Okay. All other values here and this value here are going to be greater than 0.05. Only this value here is going to be less than 0.05. Okay, so we said that n equal to 10, so 1 over 2n is 0.05. That means if this value is less than 0.05, we call it as an outlier. So you can see from the table, like all these values are greater than 0.05 except this value here, except this value. Okay, so this is less than 0.05. So clearly this data point is an outlier. Okay, so through Savana's criterion, we prove that this data point 18 is indeed an outlier. So depending on your data set, you can have multiple outliers. Okay, so as long as this condition is satisfied, then that data point has to be marked as an outlier. Now, what happens when you get an outlier? So when you get an outlier, you basically remove that data. Okay, you remove the data. Now this mean and standard deviation need to be recalculated. Okay.
Sir, I have a dot over here. I'm sorry to interrupt. So basically, for the reading that we have, like 28 to 31 in that range, only one reading was 18, right?
Yeah.
And here we could identify the possible probable outlier as 18 because data point is very small.
Mhm.
Suppose we have 100 data points for timing and dealing, and we have some readings like in the range of 50 to 53 or 50 to 54.
Yeah.
And we just plot it on the graph,
Yeah.
and we just plot two lines, which is like, if I assume that 50 to 51 or 50 to 54 is the like expected range, but I'm getting something like 60 and 70 is like that for time
Yeah.
being. So in that way also we can identify this is a probable outlier, and we can just discard it. So
Yeah,
why
that is just a guess, right? See, for example, here if it is 18 and next one is starting as 24, right? So
Yeah.
that is why you are very clearly able to know. But let's say my data points are 18, 19, 20, 21, up to whatever 29. Now, where do you mark the boundary? Okay, or let's say I had 18 and 19 and then 23, like that. Okay, you cannot always make a guess. Okay, so you do a distribution and somewhere you chop it up, but then where do you really chop? That is the question. So this basically gives you a very accurate representation of that. Where do you really put the boundary? Okay.
Okay, sir. Fine.
Now, if I had, let's say, 21 in the data point, would you call it as an outlier or not? Okay. If I had 20 or 22, would you call them as outlier or not? You will not be very certain, right? So by doing this, you will be able to really identify, because there is a criterion, and you can say that, okay, this is an outlier and this is not an outlier. You can make a guess, because in this data set, as I said, while writing, you can very well know that it will be an outlier, but that is not true for all the data sets.
For example, I was saying, like suppose we are measuring the shaft diameter for timing, and we are very sure that this diameter is 20.
Yeah.
And I am measuring 100 points, suppose, and one time the reading is coming here 23 or 20.5 or 26, where I know that the measuring that I have opted for this is grinding, and the tolerance band is so close that it cannot go to even 21.2.
Yeah.
So, if I'm a designer, if I'm making a design choice, if I'm making a process choice, then I can definitely have a very close range of what I mean to say, boundaries, where I can definitely know that, okay, 21.1 definitely is outlier in that way.
Yeah, I see. If you are lucky and you get the outlier is really, very far from the your expectations, like the example that is given here, you do not do statistical analysis, you can very well find out. I mean, I agree with you, but that is not the case all the time, unfortunately. There are situations where you are doubtful whether I should include this data or exclude this data.
Right, sir. Right, sir. Got it.
This theory becomes useful.
Okay, sir.
Clear cases, we need not do anything. I mean, any layman can come and say that this is an outlier. Okay.
Right, sir.
Sir,
Right, sir.
Sir, one doubt, sir.
Yeah.
Sir, this outlier will not depend on the data trend. It will only depend on the region.
Yeah, it will depend on your, how the data is distributed, basically. Okay. So, I mean, now the question is, when you have identified the outlier, what do you do with this? So you basically throw that data completely and recalculate the mean and standard deviation. So when you recalculate the mean and standard deviation, remember that your n is going to change and your pz naught is going to change. It may so happen that in the next cycle of calculation, you may identify that if you had 21 in the data point, or let's say it may so happen that 24 can be the outlier. Okay, so that means this process you continue until this condition is satisfied. That means I am saying that it is not mandatory that only after one cycle of applying Savina's criterion, the remaining data are all acceptable. Okay, because when you recheck again, this probability and this has changed because you have thrown the data point. Your n has become now 9. Okay, so this has become now stricter, and your probability is also going to change, right? Because when n is changing, your z naught is also changing because the mean is changing. So you need to recheck. Okay, in complicated data points where the data points are very close by, and you need to really define you need to remove identify the outliers. You need to go through this process maybe multiple times. Okay.
So just one question, sir.
Yeah.
So I got your point to identify the outlier, but my understanding is, suppose there is a shift in the data we receive, and there is a shift in the normal distribution curve itself, and maybe like most or many of the points may lie outside the specification limits. So my understanding is, before we do analyzing the outliers, we need to we need to check manually if the data we receive is beyond the specification limit, like in the sense like all of the points are outside the specification limit, or if there is a shift is there, and then we need to proceed with the analyzing the outliers. Is it right, sir?
Yeah, agree. Right. See, statistical analysis is basically a tool, and you are the best judge. If you do 100 measurements and very clearly you say that, okay, these 10 are really erroneous because it is very far from my region of interest, you must throw it out first before you actually come to use any statistical analysis. Okay, and this is just again one criterion. This is only one technique to you identify outliers. There are more other criteria also available, but we will not be able to talk all of these. If you are interested, I think if you are referring these books, Hallman and the other books, they would have cited references of research articles which would have talked about many different kinds of techniques that people can use. But in this class, we will just talk about this simple criterion. But your point is well taken, that if you are measuring and then for a target specification, you are doing measurement, and there are values which really do not conform to your specification, so you should really take them out first. But then if you have some data points which you are okay that they are confirming your specification, but then whether all of them are acceptable or not, you have to use some kind of statistical method, and this is one such method.
Okay, sir. Yeah, thanks for the clarification, sir. Thank you.
Sir, hello. Hello.
Yeah. Please go ahead.
Sir, suppose we have a large number of data points, and if a fairly decent chunk of data points are considered to be an outlier, outliers,
Yeah.
then is it possible to give a correction factor and bring it up to the mark? Because suppose this measurement is considered to be an input for some other process where loss of data points can cause inaccuracy in the next process.
Mhm.
What
Yeah.
should
See, the thing is, and you are measuring for a particular variable, right? Let's say, okay. So you cannot have a, sort of bipolar, data, So if any data point is not showing a central tendency, that means that there must be something wrong in the measurement. Okay. So we must see typically if you have some measurement and if the measurement is carefully done, they should exhibit something close to a distribution curve, right? The central tendency of data that we talked about. Okay. So I am not aware whether if you have sort of two central tendency, how do you deal with that situation? Okay, that's something I do not know at this stage.
Yeah, my understanding is, I think you're right, sir. Actually, what I learned is the reason for the error could be like related to the measurement system. We need to correct the measurement system. I guess like there are like some common cause or something like we need to identify, and then like after correcting the measurement system, then we need to revalidate or re-measure the values.
Right. Possible.
Hello, sir.
Yeah.
Suppose we are measuring when we expect some trending lines, for example, torque curve. In that case, is there a similar criteria where if we can say that this point is an outlier or there is something wrong with the measurement, or it should not be?
Yeah, this is basically a technique which is applicable to generic data sets, right? So whether you measure torque or voltage or current, length, anything, right?
So, but in that case, we have a trending line. For example, with different RPMs, it keeps on increasing then decreasing. Suppose we get a measurement which is completely out of the curve. Do we have a similar criteria to tell that it is?
No, I
something
didn't get the point then. Can you say it clearly?
So we plot a torque curve and we get all the curve is smooth and we get one point which is completely outlier, which is unexpected. So do we have a similar criteria for that? To
So
tell
what
that
do you measure actually?
torque. Suppose we are measuring torque.
Okay, you are measuring torque, right?
With respect to varying RPM.
So okay, this is an interesting point. So we are talking about here your measurement of one variable at a given input condition. Okay, that means you have basically the RPM fixed and you are taking multiple measurements. Okay.
Yes.
Now there are some measurements which are going to be, let's say at a fixed RPM, you take 10 measurements. So we are talking about that 10 measurements of torque at a fixed RPM. When you change RPM, you may make another 10 measurements or 5 measurements. So we are talking about out of these 10 measurements or 5 measurements, how many actually we should be using to find out the mean and standard deviation. See, for each RPM, you will have a mean and standard deviation, right?
Yes, understood.
That's what we are talking about.
Understand. Thanks.
You cannot just have one RPM and then one measurement. Normally, we don't do that in experiments, right? The single measurement is not active.
Yes.
At least 3 measurements you have to do, right? At least 5 measurements you have to do, or 10 measurements you have to do.
Yes. Okay. Thanks.
So one question, sir.
Yeah.
Sir, you told this criterion like it repeats for multiple time as n changes, right?
Yeah.
So in what case you should stop this
Yeah. You should
criterion,
stop.
because if you keep on eliminating data, like how will
Yeah.
we?
So you should stop only when you do not have any further outlier. Then you can accept the mean and standard deviation, right? You cannot really call mean and standard deviation of data which contains outliers. Okay. Right. So there is one more thing that I wanted to talk before we stop. That is the number of measurements that are required to ensure that your estimated value for random error in the sample mean is acceptable. Okay. So question is, how many measurements are required to reduce the estimated value of random error in the sample mean to an acceptable level. Okay. So that is, we have said that your true mean would lie in this interval. So you do some measurements and you say you find the mean, and then depending on the data, you specify the standard deviation. So this is basically the random error about the mean value. And you say that your true mean is expected to lie somewhere within this range, x bar plus minus t into sx bar. Right? This is something we had talked about. Now we define CI, which is known as confidence interval. Confidence interval. What is confidence interval? So we have this data. Let's say this is your true mean, and you have these limits. So this is plus t mu p sx bar. This is minus t mu p sx bar. So confidence interval is basically plus minus t mu p sx bar, which you can write it as plus minus t mu p sx divided by square root of n at some p% probability. This is something we have also discussed. Now this interval, confidence interval, is basically two-sided, right? About the true mean value. You have left side, also right side. Okay. And one-sided, on one side, this value is known as D. The other side is also known as D. And D is basically your precision. So D is called precision, which is confidence interval divided by 2. So which is T mu p sx over square root of n. Okay. So this is your confidence interval. Confidence interval divided by 2 is basically your precision. Okay. For example, if the confidence interval is plus minus 1 unit, or the interval width is 2 units, then your precision, or D, will be 1 unit. So from here, you can actually find number of measurements required. That is n is t mu p sx over d whole square, right? From here. So if I take n to this side, and d I bring down, and if I square to get n, because here we have a square root, then I will get t into sx d square. So how closely it reduces the range of random error to the acceptable value depends on how closely this sx basically approximate the population standard deviation or sigma. Okay. Now, if you want to find n, okay, so you have an acceptable limit. That means you have a specification of sx, and you need to know the number of measurement, but t depends on n, because this new that you want to find out is n minus 1. So you really need to iterate, okay, because somebody says that you keep the confidence interval to some value. Although you now know this, to find n you have to know t, right? So how do you find n? So one needs to really do an iteration. Okay. So, but anyway, you have to know sx, right? But to find sx, you also need to know n. Okay. So what you really need to do is that, let's say initially you do n1 measurements, and then you find out the standard deviation h1. From there, for a given d, you find the total number of measurement that is required. Let's say t n minus 1 at some probability s1 divided by d square, and here you have already done, sorry, this should be n1. Now you have already done n1 measurements, so the remaining measurements you should do is nt minus n1. Okay. So let us take an example for you to understand this. The question says, determine the number of measurements required. Determine the number of measurements required to reduce the 95% confidence interval of the mean value of a variable to within plus minus 1 unit if the variation of the population is estimated to be 64 units. Okay, so it says that you have the variance. So you have a number on the variance, and you want to ensure that the confidence interval is only plus minus 1 unit above the mean value. You want to find the number of measurements required so that the data must be within plus minus 1 unit of mean value at a 95% probability when the variance is 64 units. Okay, so that is the question. So basically here you take your confidence interval is 2 units. Okay, because that is the data. If this is the mean, you have 1 unit on this side, 1 unit on this side. So the confidence interval is going to be 2 units. P is 95%. Okay, that is 0.95. Your precision is confidence interval by 2, that is 1 unit. Variance is sigma square, that is 64 unit. So sigma is 8 units. And this you approximate as the sample variance Sx, because that is what you have used in the expression to find the total number of measurements. So n is basically T nu P Sx by D whole square. So that is T n minus 1. This is 0.95. Sx would be whole square. Now, you do not know what is n, right? You want to find n. So for that reason, you do not know what is t. But you know that Sx is 8 and D is 1. So this is T n minus 1.95 into Sx is 8 divided by 1 square. So this is n. Okay. Now how do you find n? Both sides, right? So you have to do an iteration. Okay. So this depends on the experience, but let's say my first guess is that my number of measurements is 61. That is my first guess. Then what I do, I find T n minus 1 is 60.95. So if I go to the T table, I had shown you this T table to you. So we have to find T 60.95. 60 is here, 95% is here. So this is 2.0. So T value is 2.0. Now if I substitute here, then I can find n equal to 2 into 8 divided 1 square. I am getting 256. See, this is a guess I made. From the guess, I found T. Then when I substitute that T here, I found n to be 256. So I have not really conversed. This n is different, this n is different. Now this n I used again for the next iteration. So now for the next iteration, I'll do it here. My n is 256. So now I read T 255 and 0.95. So I go to my T distribution table. and see that. So after 60, is infinity. So you have to take this value. It is coming 1.96. Okay. So this is 1.96. Now, if I find n from this formula, from this formula, then I have t is 1.96 into 8 divided 1 square. I get n to be 245. So which is different than this. So I need to iterate again. In the next iteration, I have n equal to 245. Now I find 244, 95, and if I go to the table, again same value 1.96. So this is 1.96. So my n is basically now 1.96 into 8 divided by 1 square. So I get 245. So now it has converged. So that means here it was asking determine the number of measurements required. I need 245 measurements to ensure that within a 95% probability, the mean value would lie within the range plus minus 1 unit. Okay. So anybody has any question? So you stop.
Sir, this value should be exactly matching, like 245 is equal to 245, or suppose 244.9 or 246, something like that.
Yeah.
So will that be considered to be converged?
Basically depends on your judgment, right? I mean, it should be close enough. Right?
Okay.
It have to exactly. It may not exactly match.
Thank you, sir.
Okay, so we'll stop here and we'll continue again tomorrow. Thank you very much.
Thank you, sir.
Thanks a lot.
Thank you, sir.
Thank you, sir.